So that was the insertion operation of the hash table. Actually, in the deletion operation, it can be tricky in the hash table. In deletion operation, using the closed addressing, actually it is simple. You can just go to that bucket, go to that index, and follow the linked list and delete it. And that deletion is related to the linked list issues, not the hash table. However, in the case of the open addressing, it's very complicated. Intuitively, visit the index from the hash function. If it is not there, if it is there, just delete it. If not, keep following the probing methods, and then you will find it and delete it. What's wrong with this idea? Let's just go through this example. K is indexed here, and this modulo 5 means that we have this array. It's open addressing, and we are going to use linear proving, right? So then when we insert 1 here, if we insert 1 here, it's going to modulo 5 and equals 1, so it's being stored here. And then 6 comes next. 6 is being modulo and 5, and it's going to be 1. Go to the index 1, but it's already occupied by 1, so linear proving, go to the next location, and it's empty, so 6 is being stored, right? 11 divided 5 equals 1, and then it means that still the index is 1, right? So index is 1 and move to, it's already occupied, move to the next location and then move to the next location. So 11 is being stored at the index of 3 here. So we can construct this hash table here. And then with this hash table, let's imagine that we are going to delete 6. Let's imagine that we are going to delete 6. In that case, let's just naively, we just deleted 6 here. Because we can use the linear proving, we just visit 1 and it's not there, 6 is not there, so we can visit next, move to next to 2, and we just want to remove that 6 here, and we did it. In that case, deletion actually itself is not that big problem, but that problem is searching 11 here, right? We are searching for 11, and then it's the index, original index is 1, so we go to the index 1. But it's occupied by 1, by value 1, and it's not equal to 11. So, but still there is a chance that 11 is being stored next door, because it's using linear proving. So we go to the next door, but it's being empty. 11 is not there. Then the logical conclusion is that 11 is not in the hash table. Because 11 is in the hash table, then it must be at the index 1, but it's not there, so it's taking linear proving and move to the second location, and it's not there, so right, 11 is not arrived yet. So that would be a logical conclusion, but in reality is that there is a broken chain here. Because 6 is gone, 11 cannot be reached here. So after the deletion, search can be a problem. Then how to make a successful deletion of 6? Actually, the deletion operation of the hash table often takes the lazy deletion. The lazy deletion is that just mark it and do not delete it. Means that just 6 and there is a small mark of saying that it's being deleted. And then after that, when you search for 6, you go to 1 and 6. Actually, it hits it, but there is a mark that being deleted. So it returns that it's being deleted and I cannot find it. Later, if you want to find 11 here, just visit here, it's not there. It's still occupied by 6. So there is an incentive to visit the next door and actually you can find the 11. Here the problem is that, yeah, 6 is just being marked. It's not gone. It's going to take the memory space, right? So if you keep adding the entry and deletion is not actual deletion, then there is a storage cost. It's just being there. Then, yeah, it's cheap storage. Just add up the memory space. That's one thing that you can say. But actually, there is always a limit. So whenever it hits the limit, what you are going to do is reconstructing the hash table. When you are reconstructing the hash table, you just keep inserting the hash table values and just remove the marked values by not inserting it into the new hash table. That's the approach. So, managing the hash table size, there is always a limit. Even though storage is cheap, you don't have an infinite storage. If you don't delete the entries, just keep adding more entries, then what you're going to see is that your load factor becomes very big. If you are chaining, this is the closed addressing, then this is going to go through it. So that's kind of okay, right? But the linear proving, which is called open addressing, then the load factor cannot go over 1, right? It's not using any different data structures in addition to the hash table. Chaining it makes up with the linked list. But the hash table, this open addressing, only uses the hash table space and is being created by using the array, right? So there is always a limit. And whenever it reaches almost up to the load factor 1, then it's going to go through the loop, the complexity. This is the complexity. Go through the loop. That's a problem because there are so many collisions. Whenever you are resolving the collisions, you have to spend some time, and that's very bad for the complexity. So, if that happens, you need to extend this storage space so that you can the load factor was what? Oh, sorry. Load factor was n/s, and n was the stored entries, and s is the hash table size, right? And what you want to do is increasing s here because there is nothing we can do about n, right? Or insert entries to the insert the entries to the new space with more buckets. So by adding s, we can reduce the load factor, bring our load factor down there so that we can still keep the efficiency here. But eventually what you have to do is create the new hash table because there might be some entries that being deleted, so that you want to flush out these deleted items from the hash table. So sometimes you have to rebuild the hash table from the beginning, and that will take so much time. Okay. So performance of the hash table looks like this. Is order constant, surprisingly. However, whenever the size grows and load factor becomes filled in, the case is being close to the order of n because of the proving. And chaining, in the worst case, order of n also can happen. So there is no magic here, but it's just using so much memory space to get it close to the order of constant. But in worst case, still it can go to the order of n. Here, the linked list, stack queue, and binary search tree, and the priority queue based upon tree and hash table are being compared. Up to queue, we use linked list-based approach. Up to heap, we are talking about trees. And now we talked about the hash. Major paradigm here is the linked list training and referencing. Tree was more like divide and conquer, and hash table was array and queue. This is more like linear search time, and this is more logarithmic search time, and this is constant search time. There is no silver bullet, always pros and cons, and some smart ideas that works in an average case. So just some smart ideas, and it doesn't work always, but in average case, it actually works. In extreme cases, most of them works pretty similarly. We already saw that BST can be order of n if always right-hand side is being referenced. Same thing can happen in hash table. So in extreme cases, all the bad things can happen, but in average cases, these better ideas actually improves the time efficiency. Further readings here is a great book, so please go home and read it. That's all I have, and have a good day.